Good morning. I am Amy Perlman. I am a urologist at the University of Iowa Hospitals and Clinics, and I have a very special person with us today. His name is Dr. Kletzing, Professor Kletzing. He is at the University of Iowa. Now, on his website, so he's under the College of Liberal Arts and Sciences, Physics, and Astronomy. And I feel like all the time growing up, I was always told, well, come on, Perlman, it's not rocket science. But today, it is rocket science. So Dr. Kletzing, welcome to today's STEMinar.
Thank you very much. When I have to use that kind of a phrase, well, it's not brain surgery.
Yeah, those are the two things we hear is brain surgery and rocket science. So you were born in California and then you trained in California. And what brought you to the University of Iowa and what has kept you here?
Well, it's kind of interesting. I was sort of what you might call an academic vagabond at a certain level. So actually, about a year before I finished up my PhD, I got an offer to move to the University of Alabama at Huntsville with a group there that does the kind of work that I do. And so I moved out there. I spent most of the summer evenings and fall evenings writing my dissertation and getting that all done. So I started working there. And then, I guess, not too long after that, an offer came to the group to move to the University of New Hampshire. So just a little after a year that we'd moved out there, the whole research group moved up to the University of New Hampshire. And so I was there for a while. And then in the middle of that came an opportunity. I was working on a satellite project with the Germans. And an opportunity came to go to Germany to work on the data coming back from the satellite. And so we moved to Munich, Germany for a year and 8 months. And I was working at what's called a Max Planck Institute there, which was a really wonderful time. Great hiking there and good people to work with. And actually, we were originally supposed to only be there a year, but we couldn't resist staying for another summer because it was so nice. Then we came back to New Hampshire, and then along came the job at the University of Iowa, and so we moved here. And a large part of the reason is that what I am is an experimental space physicist. I build hardware that flies on rockets and satellites, and pretty much you could say that the University of Iowa is the place where that all began.
Wow.
I work in Van Allen Hall, which is named after James Van Allen, who is the discoverer of the Earth's radiation belts, to an experiment on the very first satellite the U.S. ever flew, which was Explorer 1. And so this is really kind of a place to be. My wife is a professional musician. She plays bass, upright bass. And so it's turned out that here, there's very good, music scene of all types. Her primary kind is classical. But so she plays in Orchestra Iowa, which is based up in Cedar Rapids and teaches at 2 or 3 of the schools here in the area. And so it's just turned out to be a remarkably nice fit. And what we find is Iowa has a lot of the advantages, I guess you could say, of a somewhat bigger city. We have nice restaurants and things like that. Yet I can walk to work every day, which I do. And so other than that white stuff that comes out of the sky in the wintertime, we find it quite comfortable. When I grew up, you drove to the snow.
That's right. So we have a lot of students on the call. And for the students who are on the call, if questions come up or you want to make a comment, feel free to type that into the Q&A, that chat box, and we'll make sure to address it during today's STEMinar. So, okay, when you were, let's say, middle school, high school, what did you think you were going to be when you grew up? And when did you decide to do what you do?
Well, I guess one major influence is I was a huge fan of science fiction. And so I read lots and lots of science fiction, all the classics and things like that. And so kind of, towards, middle high school or so, I probably started to realize I wanted to study physics because I figured if space travel was ever going to happen, it was going to come about because of physics. But the interesting thing is I was also very involved in theater because I did technical theater, I did lighting. And so, my high school had quite a sophisticated program in that, with a big summer program. And the last year I was, before I graduated, I was in charge of the whole lighting scheme for this, 3 big plays that we did in the summer and things like that. And so my senior year, I submitted one of my lighting designs, and I actually won a theater arts scholarship. So I started at UC Berkeley on a theater arts scholarship. I knew I wanted to study physics, but I waited till I used up the money before I declared my major.
Right. So,
Um,
how can people in high school now, like, what should they be getting involved in to further explore their potential interests in perhaps physics, engineering, math, technology?
well, what I usually tell almost anybody is keep taking math.
Hmm.
You know, math opens up doors to all kinds of disciplines, be it engineering, be it you know, medicine, be it physics, or you know, biology or whatever. You know, the sciences and even the life sciences, there was a time when you didn't need much math. That's not true anymore. And so at a minimum, you want to get up through calculus, I would say, simply because you know, physics, chemistry, and biology have moved much closer together than they once were. I mean, you see this in the Nobel Prizes. You know, a chemist will win in physics, and a physicist wins for, you know, some process that affects the life sciences and things like that. So I think math is really the door. And then I would say, you know, don't be afraid of subjects like physics and chemistry. Dig in, find what you like about them, and study those, because they inform what you will do in any of these kinds of different professions downstream.
Yeah, that's so interesting that you bring up math, and I don't do complicated math in my current work as a physician, but every single medical device that I use in the operating room is not, it seems very, products that I use, it seems like they just, someone puts them together in a mold and they show up in my operating room, and they're so technical. Every little piece of that device has some sort of underlying engineering, physics component, chemistry component. And so I wish I could go back to high school now and maybe retake some of those classes to better understand what I do on a day-to-day basis at the most basic level.
Well, I think that's a really good observation, because the more you understand about the device you're using, the more you also understand where its limits are,
Yeah.
and what could potentially be, you know, something funny about how it's giving you data back or whatever. And so, you know, like many, pretty much everything in life, the more you understand about it, the more you appreciate it, and the better you can use it.
Yeah, awesome. So your research focuses on measuring the plasma environment of the Earth's magnetosphere. What does that mean? What have you learned from your work?
So well, so we need back up a little. So
Yeah.
you know, there's this big glowing ball in the sky called the sun, and it spews out a constant rain of actually we call it a wind, the solar wind of particles that come towards the Earth. And the Earth has a magnetic field. You know, that's why our compasses work and so forth. And so when that solar wind comes across the Earth's magnetic field, it gets deflected by it. And so it creates sort of a bubble, if you will, around the Earth, where inside the Earth's magnetic field is strongest and dominates everything, and then outside the sun's solar wind and sun's magnetic field dominate. So that region inside is what we call the magnetosphere. And it's pretty interesting because it gets really squished in on the front side of the Earth, and it gets dragged way, 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 way downstream. So we talk about, you know, day side is close, and then magnetotail goes way, way, way far away. And so there's a whole huge variety of phenomena that happen, because with that solar wind represents a lot of energy coming at the Earth, and it couples in and it causes all kinds of phenomena. Probably one that I've studied a good bit, not so much now in my career, but earlier, is the aurora borealis, or the northern lights, which actually, surprisingly enough, many people in Iowa have seen.
Hmm.
Uh, because not often directly overhead, they'll see it to the north, but because we happen to be close to or further north in a magnetic sense relative to the Earth's magnetic pole, you can see it. And so that's kind of one end product. Another thing is, you know, we study the environment, the Earth's radiation belts surround the Earth, and we have a lot of satellites out there. People kind of forget how much we use space these days. You know, there was a time when there's this big paper thing you would unfold to figure out how to go to places. And now, you know, everybody uses one of these. Well, this is basically taking data from a satellite to tell you where you are. And so understanding that environment is really important to, you know how to build satellites that can withstand it. Virtually all of the television that you watch comes through a feed that comes from a satellite sitting out of what we call geosynchronous orbit. So we actually use space a whole lot. And so my work up until about 15 years ago concentrated heavily on the aurora borealis. I still do some work in that area. More recently, we've been working on the Earth's radiation belts. We've flown a pair of satellites called the Van Allen probes, named after Professor Van Allen, and they explored the radiation belts in the most detail that's ever been studied before. And we've learned a lot about what creates them, what destroys them, and how to understand when to be careful about things that we send out there. And right now, I'm building up a new mission that will study a different region called the Earth's cusp.
Wow. Okay. So talk to us about your current work with NASA. What questions are you specifically trying to answer?
Okay. So we are in the early phases of building up a mission called the Tandem Reconnection and Cusp Electrodynamics Reconnaissance Satellites.
Wow.
That's tracers. We often joke you have to have a good acronym or you don't win a NASA funding. And so what this is a pair of small satellites. They don't go that high. They only go up to about 500 kilometers, about 300 miles. But they will be orbiting the Earth, and they go through a region on the front side of the Earth. And when I say front side, I mean on the sun side of how the Earth happens to be oriented, called the cusp. And this process I was talking about, how the solar wind injects energy into space around the Earth, depends on a fundamental thing that's called magnetic reconnection. And we won't go into the details of that because I'd have to go to the blackboard. But the interesting thing is when that process happens, things move along the Earth's magnetic field lines into this region called the cusp, and it almost acts like a little television screen of the phenomena that are going on. And so there's a couple of outstanding questions that have been around for more than 25 years that we haven't been able to answer because you need two satellites that are closely spaced going through there, and that just hasn't happened before. And so we flew a pair of rockets a couple years ago, and as we were just starting to get going on that project, one of the scientists I was working with said, hey, we ought to propose this as a satellite mission, because with rockets we get one shot at it. With the satellite we get 9 passes a day through this region. And so we're going to answer this fundamental question about how does that energy couple in, and does it happen in multiple places, or is it something that turns on and off with time? And we don't know the answer right now. And so that's what's kind of the neat thing about what you can do with some small satellites sometimes is you can answer big questions, but you don't necessarily have to spend huge amounts of money, although most people gasp at the amount of money even 2 small satellites cost. But compared with the big missions, they're still pretty inexpensive.
Yeah, and I think the work that you do really exemplifies the importance of teamwork. So who are some of the other people that are on your research team here and at other sites?
Oh, so it's a pretty good sized team. I mean, not huge though, not as big as like our super big missions. But here at the University of Iowa, I'm collaborating with people here in our department. And so one of the science instruments that will make measurements of electrons coming down towards the Earth is Professor Jasper Halligus. And he's been in our department for about 6 or 7 years now, I lose track. And another is George Hospodarsky, who's building what's called a magnetic search coil that measures magnetic waves. And so those two will both be built here. And then my group is leading the project. So Scott Ballens is doing what we call project management for the instruments, all the different instruments, to make sure that people are staying on track and getting things done, and we're answering questions. And then there's another guy named Jeff Dolan who does what we call the system engineering. So he kind of does the technical side, and Scott does more of the making sure that things are being managed. And then we also have Carol Preston, who does all the accounting and watching the money and all those kinds of things. And that's just here at the University of Iowa, and we've got some students involved in things like that as well. But outside of the University of Iowa, we're partnering with the University of California at Berkeley. They're providing us an electric field experiment. University of California at Los Angeles is providing the magnetometer, which measures the background magnetic field of the Earth. And then we're partnering with Southwest Research Institute, which is providing an instrument to measure ions, as well as they're providing the overall project management for the project, because they have a number of tools and things like that that help us do that. And then on our science team, we have a professor from Dartmouth University, a professor from Auburn University in Alabama, another research scientist in Colorado, Boulder. And then our spacecraft is being built by a place called Millennium Space Systems out in El Segundo, California. And our project system engineer, and this is the person who watches over all the technical aspects of the program, is a place, runs a place called Bison Aerospace out in Wyoming. So it's really kind of a far-flung team all over the country. shall we say, we've been doing a lot of meetings on Zoom.
So we have a question, and the question is, do you use CAD and CE to help design your missions?
Absolutely.
So
Yeah, I
what
mean,
does that mean? What is
uh,
Nikolai referring to
CAD
there?
is computer aided design, and it's kind of a rubric, if you will, for you know, well, both on the electrical and on the mechanical side, that you use a computer to do all your drawings, and you know, we'll do the dimensions and all that kind of thing, and make sure things fit together. On the electrical side, it's usually using a schematic, and then that gets turned into how you lay out a printed circuit board, and how you assemble it and things like that. I mean, and pretty much in engineering, these are standard tools today that everybody uses. And then we also use it, you know, let's say when we're manufacturing things in our shop. I mean, those are also use computer controlled machining as well, because the accuracy and the repeatability you get with that versus, you know, just some guy looking at a print and making the part is much better. So yeah, the modern tools all have to be used on this stuff because we need a fair amount of precision to make everything work.
Okay, awesome. So for students that are, let's say, now in high school, when, if they're interested, when can they start getting involved or reach out for internship opportunities for this type of work?
Well, there are programs at the University of Iowa that get students involved in the sciences broadly, and I would encourage them to look at that. However, once they get here as a freshman or a sophomore, particularly if they're in the physics department, they often come and, well, maybe not in the current environment and knock on my door, but many of us use undergraduate physics students in our research. I've done this for years and years, and there's lots of opportunities. And in our department, this isn't like little make work projects either. I mean, we need to get something done. We pay you to do that, and usually we pay reasonably decently. And so, you know, this is the real deal. You know, you're in charge of getting, you know, this little part designed, or, you know, writing a computer program to do some data analysis or whatever we happen to need. And so that's what I encourage students to do. And this, I think, is true across all the various sciences that you might get involved, is, you know, get out there, meet your professors, and see if they've got some work that you can do. Because there's lots of opportunities. And I think that's one thing that's good about the University of Iowa, is that there are those kind of opportunities to get involved in research. I mean, really doing it, not just, you know, some little project that I could think of that, you know, well, I don't really need it, but here's something for you to do, because we don't do that.
Yeah.
You
So
got to do something.
a lot of what I'm hearing from you is really exciting to me, but what excites you about where you envision this whole program going in the next 5-10 years? What gets you up in the morning?
Well, I mean, I didn't become a professor because I didn't like to teach. I do quite a bit. I still enjoy it. I often teach the big introductory classes. In fact, I have one this semester and next semester as well. Be that freshmen in the sciences, or people that are going into the health professions. I still find it a lot of fun to talk to students and show them how this stuff works, and to demonstrate that, you know, physics really informs almost anything you do. I mean, it's really kind of the study of how the universe works. And I try to also illustrate in my class that this stuff is actually useful to you, and even in everyday life. And so we do various examples of things of that nature. And I think, you know, understanding even some basic ideas can, you know, let you understand, you know, if you're looking at a rainbow, I try to talk a little bit about how does that work. And or we're talking about mechanics, you know, how does the stress on a bone work and things like that. So we'll bring those sorts of things up in class, or I'll assign a homework problem for you to do. So I like the teaching part a lot, and I like to balance that with the research, because there's, I enjoy leading a team, and I also enjoy doing the science and getting in and finding new things that other people have never seen before. Or maybe they've seen it, but they didn't realize that this had some relationship to some other quantity, and so we can figure out things. And so research is really the creation of new knowledge. And at a certain level, that's, you know, exciting in and of itself. So, you know, that mix of things is why I'm a professor, because I like to do both. I like to do the research, I like to do the teaching.
Yeah. All right. So let's summarize here. You brought up a lot of great points. So what I'm hearing from you is math is important. And even if someone has some sort of interest in any of the sciences, you know, you encourage people to take as many of these classes as possible to really explore what that field has to offer, because it's not physics and chemistry and math. Everything is actually the same thing. We just slightly nuanced. Is that what I'm hearing?
Yeah, well, what I tell everybody in my class is that really chemistry, biology, that stuff, it's just applied physics.
Yeah. Okay, awesome.
And the other thing is, I would back up to the math again, even if you don't go into the
Yeah.
sciences, business, if you've got good math skills, you're going to be in good shape. There's just almost no part of life where if you've got good math skills that you aren't going to find that to be beneficial to you.
Yeah. And I'm going to add one comment to that: math skills and writing skills.
Yeah,
Being able
I
to
forgot
write
writing.
well is so important. And I remember I learned to write well in my 8th grade English class because my English professor, she was a stickler. She was really tough, but that's where I learned to write. And I use those skills all the time in my current work.
Oh, I should have mentioned that. We don't do as much of the writing in physics classes, but when I have physics students and they're asking me to advise them what to do, I say take writing classes, because I would say in my research work, probably at least half of the time I'm writing things of one sort or another, be it a paper or a proposal or email describing something to somebody. I mean, there's just all kinds of written communication that goes on. And just in much the same way as math, the only way you get good at writing is by practicing.
Yeah.
It just doesn't just magically happen. And so when I was going through college, I had my senior year a really good English professor or English teacher, I should say, that kind of beat me up over my writing. Kind of threw me back because I was used to doing really well, and no, this isn't very clear, things like that. And it took a while to get good, but I took lots of writing classes along with the physics. I mean, I like to take English classes and philosophy classes and things like that, but they always had a writing component, and so I stuck with that. And it does matter. The better you can express yourself via written communication, the better off you'll do. And again, that's across all disciplines. People that are good writers are successful people.
Yeah, absolutely. And then some of the other points are, especially at Iowa, plenty of opportunity, whether they're an undergrad high school getting involved in STEM seminars and such, like what we're doing today, undergraduate knocking on the professor's door, sending them an email and saying, hey, I'm really interested in following through with that work. So a lot of great opportunities. Are there any other points that you want to make for those tuning in?
Well, just that, like I say, don't be afraid of some of these things. And also, in high school, your subjects are a little bit more prescribed. You must take these things. But when you get to the university, you have to take what we call general education requirements. And I always tell students, don't just take everything that, your buddies are taking, or because that's supposed to be an easy class. Think about what you might be interested in that you just, you're curious, but you don't know anything about it. Like, let's say you've always been interested in sculpture. So, take a sculpting class. Why not? It'll satisfy a requirement, and you get an opportunity to work with a professor who's an expert in this area and show you something about that and maybe learn a little bit. Now, you may say that was enough for me, or you might find it something you really love, or if nothing else, just if you're ever in a museum or something, there are more things you can appreciate about that because you can see what the work was that had to be done. And this applies to, if you're interested in theater arts, if you're interested in history, if you're interested in poetry, there's a whole wide range of different topics. And so I always tell people, look around and find something that really interests you, because you'll get a lot more out of it. And it's kind of a golden time when you can explore different things that you might never get the time for once you're in the working world. So that's the other piece of advice I always give is poke around, because at a university there's so many different things. I know when I graduated, I still had a list of things I would have liked to have taken, but at some point they kick you out because you got enough semester hours and you have to go on.
Yeah, and you're right. I mean, this is like a place where you have experts in each of these fields. And once you get out, and I won't even call it the real world, but we are living in the real world, even people in undergraduate, but this is, at what other time in our lives will we be in an institution where you have so many experts all in one area, and we can literally reach out to them via email. We have access to really anybody.
Yeah, and classes that are organized. So almost every department offers what we usually call non-major classes.
Uh-huh.
So I remember I've always been interested in theater, so I took a Shakespeare class. I had no idea that it was designed for not majors, so it wasn't the full thing that the English majors had to take. It was a great class. We saw lots of plays and movies of the plays and so forth, and it was like, wow, what a great class. And so looking around for those little nuggets of what interests you, it's like I said, it's a golden opportunity, so use it.
Yeah. Awesome. Well, I appreciate your time today, Professor Kletzing, and we're going to wrap up this seminar. This will be posted on our various social media accounts, so you can watch it again, you can send it to other people, and we look forward to our future seminar events. And again, I appreciate your time this morning.
Oh, my pleasure. I always like to talk to prospective students.